So we've talked about how to do principal component analysis, and in this lecture, we're going to finally do a bit of it. We're going to have a little bit of a theoretical roundup first. So if you really can't stand those bits, just scoot on forward until you start seeing code up on the screen. And we're going to do some example code using two different languages today. We're going to use both R and Python. I think all the other lectures we're going to use R. So this is sort of a nice little treat. All right, let's get started.
I want to remind you of what we've seen of PCA so far. Just want to sort of lay out the key points from the last lecture because it's easy to forget them and we should just see them a few times, I think. So the idea behind PCA is that you take data originally in some form of a matrix X and you transform X. So transform the data X to the following. So the transformed space, or the PCA space, or PC space, if you want to call it that, is the Y matrix. And that's given by the X matrix times this so-called matrix of loadings, A transposed. And A transposed looks like this. Its columns are made out of the eigenvectors, like that, and so on, up to the last one, P. I think in the last lecture I was mistakenly saying N for the maximum index of the eigenvectors, but N was meant to be the number of observations. It should have been P, which is the number of features or variates that describe the data. So A transpose looks like that. And those alphas are the eigenvectors of the covariance matrix for X, right? So the alpha hat I, they're the unit eigenvectors, are the unit meaning have length 1. So they've been normalized. That's another way to say that. They are the unit eigenvectors of the covariance matrix for X, which we call sigma, and that's 1 over n minus 1, and then centered X transpose times centered X. Yeah. And the elements of that thing are the following. So the elements of the transformed matrix. So Y, J, K is equal to this dot product. So it's the dot product of row J of the matrix X with eigenvalue K of the covariance matrix. And again, the eigenvalues are listed in decreasing order of their corresponding eigenvalues. The eigenvectors are ordered in decreasing order of their corresponding eigenvalues. Okay, and so this quantity xj dotted with alpha hat k, you could interpret this as the projection of observation j onto principal component k. So that's what each one of those is, the different elements of the Y matrix. You can also use the lingo that they use in this field, that this is observation J's kth score. So that's some lingo there. And yeah, I did write already, but I'll do it, or I said it already, but I'll write it again. So A transpose, or the matrix A by itself, I think people use it either way, is called the matrix of loadings. This is just some terminology. It's also sometimes called a rotation matrix, which makes sense. And I'll just write down the rule about how we order the eigenvalues. So the one that I said out loud, but so this is the statement that the alpha hats are eigenvectors and that our eigenvalues are lambdas. And the rule is if I is less than j, then eigenvalue lambda I is greater than eigenvalue lambda j. I'm putting absolute values here around them because eigenvalues can sometimes be negative, but you'll see in the next line that there's some problem if one of your eigenvalues is negative here. There's sort of a problem with that. Okay, so the reason for that is that the variance down column K, so this notation means column K of the Y matrix, is given by, there's sort of a simple way to write it and a little bit messier way. The messier way is this product, so it's alpha K transposed times the matrix sigma times alpha K. Or, more simply put, that's just equal to lambda K. And we showed all those things last time. And so you can see why it's problematic if one of the lambdas is negative for us. It does happen sometimes, though, and then you have to kind of make sense of what that means. It usually just means trouble for us. Not generally. It's fine to have negative eigenvalues generally, but okay. So we're going to go through a little bit more theoretical stuff today, not much, and then we're going to do a bunch of examples, which I think you'll find fun. So the last kind of claim or theorem type thing I want to introduce will happen now. So claim, I think I made 2 before, so I'll call this claim number 3. Or if you want, surprise number 3. I only keep writing the word surprise because I want you to remember that it's not supposed to have been obvious, any of these claims. Excuse me. The fact that these things are true sometimes is presented in such a way that the student is left thinking like, yeah, I was supposed to be able to just see that and know that. And then you start feeling ashamed of yourself because you didn't. And so you get in the habit of just accepting all sorts of crazy things, thinking like, yeah, I should have saw that. But this is not the case. So these are not things you should have been able to see. Okay, so here's the claim. The columns of Y have 0 correlation. In other words, the columns of Y are independent. Okay, so let's look at a proof. This proof is relatively easy. I think there might have been some mathematical goofs in my last proof, the one where I skipped a bunch of steps involving the Lagrange multiplier. It's a correct statement, and I think I just mangled a couple of the steps where I was skipping steps. But hopefully you were able to work through those and see that. If not, you can get in touch with me and we can try to go through it. Okay, so here's how the proof works. So the idea is to show that the columns of Y have 0 correlation. And so in order to do that, we're going to want to look at the correlation matrix for Y, right? So last time we saw the following. We saw that the correlation matrix for Y could be written as A times sigma times A transpose. All right? So that's where the correlation matrix for Y is, by definition, sorry, that's supposed to be a Y. It's 1 over n minus 1 Y-centered transposed Y. But we showed last time that you could express that in terms of the loadings matrix and the covariance matrix for X in the way that you see here. And so let's take a look at the kind of details of that matrix. So if you look at sigma times A transpose, right? So that's the matrix sigma times, and then I'll use my funny notation. So all these columns, alpha hat 1 up to alpha hat p, again, where p is the number of variates. And then if you distribute, when you do the matrix multiplication here, it's similar to, the process is similar to just distributing the sigma through the matrix and multiplying it by each of the vectors one by one. And when you do that, because the alpha hats are eigenvectors of the sigmas, you get a simple result, right? So you get the first column, when you multiply sigma by alpha 1, you just get you just get lambda 1 times alpha hat 1. And that's your column, where lambda 1 is a scalar. And then that process repeats, and for the last column you get lambda p times alpha hat p. And so that's how that matrix multiplication works. So we essentially have seen how the covariance matrix kind of disappears and just turns into a bunch of constants that weight the columns differently. So when you look at the overall product, A times sigma times A transpose, well, that looks like the following. So we'll write down the matrix A first. So that's alpha 1 transposed, and that's a row, right? And that goes down to alpha p. So it's p different rows here. And then that's multiplying this matrix we just wrote, and so I'll just copy it because it's kind of lengthy. Like that, right? And so you can multiply each of these things through. I suggest you just do the following. You look at what happens when I take this guy through and hit this matrix with it. What do I get? Or this column with it. Row, sorry, this row. Sorry. So what happens when I take this guy, this column, and combine it with this row, and then repeat it down the line. So then this column down with the next row, all the way until you get this column down with this row. And then you move on to make your second column of your result using the second column of this guy and repeat that process, right? So let's just look at one particular element. So we'll look at A sigma A transpose row I column J. Okay, so that means I'm going to take, how do I write it? So I'm going to take, among these different rows, I take row I, and among these different columns, I take column J. And so what I get is alpha hat transposed I, and then lambda J, alpha hat J. And of course the lambda is just a scalar, so it can be moved out to this left. So I've got lambda J, and then what I have here is the product, a dot product, right? So I have alpha hat I dotted with alpha hat J. But these two, these eigenvectors, these vectors, the alphas, these, if you remember right from yesterday, or from, yesterday's lecture, these are orthonormal. They all have length 1, and they're all orthogonal to any of the other ones in the set. And so this quantity, this calculation, is just equal to one of two different things. It's equal to lambda J if I is equal to J. All right, so that means if we're looking at one of the diagonal elements of this matrix here. But if you're off diagonal, which means you're looking at covariances between two different columns, it's 0. Because I is not equal to J, and you would be taking a dot product of two different orthogonal eigenvectors. So this is nice. This means that, and so this matrix on the left, right, this guy here, that we're looking at row I, column J of it, if it obeys this rule here, it's just a diagonal matrix, and that's sigma y, right? So if you go back up here, this is the thing we were analyzing. So what we find is that sigma y is diagonal, and its elements are lambda 1, lambda 2, and so on, up to lambda p. And all of its off-diagonal elements are 0. And so that proves what we were after. It proves that the columns of the matrix Y are not correlated because all their covariances are 0. The variances are the non-zero parts, and those are the eigenvalues. Okay, I'm going to introduce one last concept, and then we'll just summarize everything and go to the code. And the last concept I want to introduce is total variation or proportion of variation, which I think you probably have used before in other contexts. So total variation and PCA. Right? So let's say we focus on the eigenvalues, which are the variances along the columns of Y. So if lambda k are the variances, or are the eigenvalues, sorry, are the eigenvalues of sigma, then the following is true. The trace, this is a rule we saw before, the trace of sigma is equal to the sum of all of the eigenvalues. So the sum of k equals 1 to p of lambda k, right? And that's nice to know because you can compute the trace of sigma without finding the eigenvalues. You can just add up all of the diagonal elements, which is what the trace does. And since these are variances, so since lambda k is the variance along column k of Y, then the following must be true, that the trace of sigma is equal to the total variation or total variance, I'm not sure what term you might want to prefer, of the principal components, or on the principal component axes. Right? So the trace of sigma gives you all of the variance in the Y space, right? And you can look at the kind of proportions relatively easily, right? So the kth PC axis, the kth PC's proportion of variance proportion of total variance or total variation, proportion of variation is then the following. So we'll call that P sub k, different P from the one that labels the number of variance. So you have to be a little careful with that. And so that's just the variance for that one column divided by the total variance, so the trace of sigma, right? Or you could, if you wish, you don't have to reference sigma at all. It's lambda k divided by, this is probably maybe the easier one. If you've already found lambda k, you have the other ones too. So sum over I equals 1 to p, let's squeeze that in there, of lambda I. All right, so that expression gives you the proportion of variance explained by the spread of the data around on principal component k. And that's a kind of a useful result, right? So you can also just write a cumulative version of that. Sorry about that. The first m principal components they have a cumulative, so have cumulative proportion of variance. That's given by the following. So we'll use a different notation for that. Similar one though. P with a superscript of m in parentheses. I'm not sure how universal that notation is, but it's used, I think, in our notes, and so I'm using it here. Or maybe it was in one of the books where I saw it. I can't remember. And so this looks like a sum k equals 1 to m of p sub k, right? And of course, you can translate that into the lambdas, where you write what you had before, but with a sum in the numerator and the denominator. So a sum up to m in the numerator. And in the denominator, sorry, I should have used a k up there. I guess I'll use a k on the bottom. The denominator, you sum over all of the lambdas. Like that. Okay, so I think now we have seen all of the particularly useful elements, for me, as far as I'm concerned, of principal component analysis. We will revisit various pieces of them and go through them a little bit more in the context of examples as we go forward. But I just want to, excuse me, I just want to summarize these properties because I think it's really important to remember what they are. So main PCA properties. And we wrote this kind of thing before, but I'm adding to it. So these are the main PCA properties. I'm going to highlight this. I'm going to make a little box, all right? But item 1 in the box is that the unit eigenvectors of the covariance matrix, so alpha hat I of the covariance matrix, which obey the following rule, right? That's it, because they're eigenvectors. And then we're doing the convention I in order of, how do we say it, decreasing we should just put lambda I, but just to be sort of extra cautious, I'll put absolute values around there, even though, as I said, negative ones are sort of problematic for us. The unit eigenvalues of this guy point along the ith PC axis. I should make a comment here as well. They do point along the ith PC axis, but there's two ways to point along the axis, right? If I said draw me an arrow that points along the horizontal axis after having drawn a two-dimensional plot, you actually have two options, right? You can draw one going in the direction in which the axis increases, or in the direction in which it decreases, and both of those point along the axis. And because of that, we'll see some unusual, or maybe hopefully not at this point, because I'm mentioning this, some sort of unexpected discrepancies between different methods, where one method's unit eigenvector points in precisely the opposite direction as some other method. And that's fine. That is, there's a freedom for that here, because this statement here points along the ith PC axis is sort of open-ended, right? There's two versions of along. Okay, so that's property number 1. Property number 2 is that lambda I is the variance of the data along that axis, along axis I. All right. 3, all of the PC variants or columns are independent. So these are columns of Y. Are independent or uncorrelated. It's a pretty powerful result. And then 4, property number 4, which is the last one I want to list, is just a statement about the cumulative or the proportion of variance. So PCK is responsible for the following amount, P sub K, which is lambda K over trace of sigma. Or we've seen it written the other way as well. So this is lambda K over the sum I equaling 1 to P of lambda P for that proportion of variance, or proportion of total variation. Of the data. And I hope that it's clear to you why this is useful, that little result, because it means that if you wanted to start throwing out different principal component axes, you would know exactly how much you're losing. So I'm going to put a box around this because it's pretty important. And again, we went through some proofs, some more difficult than others, but proof or not, understanding the proof is one thing, which I hope you all do, but more important is at least knowing the results. So as sort of a secondary goal, a lower level goal, if you wish, is at least knowing what the proofs actually said. Sorry, I put that back to normal size. So these are the main principal component analysis properties that we have so far. I guess I may add some things to it, but I think this is a pretty hearty list of properties for us to look at. All right, so now I'm going to go to the code, and so we're gonna try to do some principal component analysis today. And the first thing we're going to do is we're going to use this command called Datasets. So I'll run this, and this is it brings you a command called data parentheses. And that thing has a whole bundle of different data sets in it. I think you guys might have already used this before, I don't know. But if you haven't, there's a whole slew of different data sets in here to kind of play with. You could use these for your project or other tests when you want to try out new methods or something like that. I just thought I would show it to you in case you didn't know that this was there. It's handy. So, for example, like here's one, Titanic, survival of passengers on the Titanic, and I think you may have used that one in many of you will have used that one in the lab or in the classes for ID 5059. So we can take a quick look at that one just to see what it looks like. We're not really going to do anything with it, but so that command brings it into my space. And I can say, tell me about it. And it'll give you a little description of what's going on there. So it talks about the survival of people on the Titanic and has various data about them, their gender, their age, and so on. And so you might find this kind of handy if you wanted to play with this data. I think it might be that you use a different source for the Titanic data in 5059. But yeah, you might want to know that it's there. So okay, now first I would like to actually get rid of it. You don't want to have a lot of extra data hanging around. These are not big data sets, but still, if I do ls, it tells me what stuff I have in memory, and that's Titanic, and I want to get rid of it, and I'll verify that I got rid of it. This is just good bookkeeping, making sure that you have thrown away stuff that you're not using. This will matter when your data sets are big. You don't want to have 10 or 12 copies of a 15 gigabyte data set laying around if you don't need to. Okay, so the data set we're going to work with today is called IRIS. It's a very famous data set. I think it will also come up in ID 5059 for those of you who are taking that module. So the first thing I'm going to do is just ask how big it is. And it's not gargantuan. It's got 150 rows and 5 columns, so that's pretty good. That's a good practice data set size for a multivariate analysis class. And let's have a summary of it to see kind of what's in it. So these are the first 4 columns up here and the 5th one down here. So these things, first 4 columns are describing properties of flowers, irises, or maybe plants, I guess, I don't know, some kind of plant data. And then this is just the usual like statistical information about it. And that last column is species, and that's just a string telling you which of the 3 different types of plant are there. What was the particular entry. So there's one called setosa, there's one called versicolor, and one called virginica. I'm not sure if I'm pronouncing those right. And there's 50 of each of those. And you can just explore that 5th column to make sure you kind of understand what it is. So it looks like this, just reads like the first 10 elements just read like setosa, setosa, setosa. So actually all first 10 are setosa. But if you click this levels thing, it'll tell you what other levels are available. So these other 2 things are there. Now we'll do just a little quick EDA stuff. So look at some plots of it. So we'll make a so-called pairs plot. And some weird stuff should happen for the 5th axis, and it does. You see this kind of strange, discrete stuff happening. But the more numerical information here, that's kind of what we're focused on. So rows and columns 1 through 4. These are the properties of the plants. And you see that the properties kind of lump into 2 different lumps, at least for a lot of these squares. So there's really 6 interesting graphs to look at here. Remember, these down here are redundant. And in each of them, there seem to be 2 lumps of data, right? In each of those 6 plots. And so we can try to explore, see if we can understand that. So here I'm going to make bivariate plots, but I'm going to label a one property versus another. So like one of these pairs plots here. But I'm going to label each of the points with the name of their species. So we'll do that. And so it looks like the virginica stuff is mostly up here. Setosa seems to be the lump at the bottom. So this is petal width versus sepal width. So that's which one of these, petal and sepal. So that's got to be this plot here, or this one, depending on which order it's in. Looks like it's this one here. And you see that the virginica and the versicolors are sort of smushed together into a pile, and setosas seem to be off by themselves over here. This different species of plant seems to have smaller petals but longer sepal widths. Okay. Now I'm just going to strip off the categorical information and be left with only the first 4 columns. So I'm going to call that result numerical iris. I probably should use an arrow here. This is just an artifact of me being resistant to R. But I think actually nothing will happen, so we'll carry on with that. And then we'll just double check that this is actually what we wanted. So here's the pairs plot, right? You can see only the 4, so that did work. And now we'll do our very first principal component analysis on this guy. All right, and so we're just going to use this one command called princomp. We are going to use another command for principal component analysis later in this thing. And we're going to see some differences. But in any case, we'll start off with this one, print comp. And the result we're going to store in something called PCA iris. The dot is just for naming. It doesn't have any functionality there in PCA.iris. I should remove that. That's an R-ism whose time has passed. Okay, but so what did we actually calculate? So let's look at this. We'll look at the summary of PCA iris. And this is saying I want to see the loadings, right? Oops, let's see what happened. Did I not make it? Oh, I didn't make it, yeah. Excuse me. There we go. Okay. And so here we've got, okay, now let's see if we can make sense of what we're seeing here. So it says importance of components is one piece of information, and loadings is another piece of information. So the loadings should be the eigenvectors. There's 4 different columns. Some of the elements are blank, and that blankness, I find it kind of frustrating. It's when values were deemed too small to pay attention to. And you can force them to show those components, and we'll do that in the next box. But let's look at this top thing. So standard deviation, so that's going to be the square root of the variances. Proportion of variance, and then each of these for 1, 2, 3, and 4. And then cumulative proportion of variance. So for number 1, the first principal component explains 92% of the total variation, which is pretty amazing. So maybe you could analyze this data using only just one principal component, which would make it a univariate problem. No, it's not that principal component is one of those things, petal width or sepal width or whatever those are. It's some amalgamation of them, right? And it goes off in the direction of the greatest variation. And that explains 92% of the variation. If you went to the next, added 2 dimensions, so you made it a bivariate problem, you've got 98%, and so on. So you can see there's really very little reason to ever add the 4th, or at least if you're just going by this, there seems very little reason to ever add the 4th principal component analysis, or principal component axis. Okay, so here's this bit where I force showing me the components of the vectors, and so here now I can see them all. So this thing it deemed too small, minus 0.08, and that doesn't strike me as super tiny, so I don't like that it did that. I mean, it would be if the other ones were 100 or 2 million or something like that, but they're not much bigger. 5 to 10 times bigger. Okay, and let's see, do we have different information down here? The loadings are there. Yeah, so this time, instead of getting, so what did I do differently here? I didn't say loadings equals true. And I'm just printing PCA, yeah, so this is what's happening. I'm just printing the loadings. And so what I get is the loadings, but I also get this other thing here, which tells me something about the proportion of the variance. And now this is kind of interesting. I'm not sure, this is quite different from what you see over here. So this makes it look as though, and suspiciously as though, each different thing makes up a quarter of the variance. And I think this top row is talking about probably the norm of the vectors, which is 1 for all of them. So I'm not really sure what's going on with these 2 lines down here. They seem a little suspicious to me. But yeah, so that's how we use, which was it? Which one did we use there? Prin comp, right? And now we're going to check to make sure that some of these things make sense, all right? So you know how to calculate eigenvalues and eigenvectors. We did that in the first computing practical. And so you should be able to check those things, right? So let's print the standard deviations that we got from the print comp calculation, right? So those guys are there. And we should be able to make sense of those as the square roots of the eigenvalues of the covariance matrix. So this will calculate the covariance matrix of the numerical data. We'll call that sigma. we'll get the eigenvalues stored as, or eigenvalues and vectors stored as EV. And then I'll just look at the square roots of the eigenvalues and see how they compare. So I'm comparing these guys and these guys. And so they don't look precisely the same, but they do look similar, right? So 2.049 compared to 2.056. So there's some difference, that's enough difference for me to think that there's something up and we should kind of explore around and figure out what's going on. But let's carry on anyway. So this last one looks pretty good. This is good to like the first 5 digits or something. Let's look at the eigenvectors and see if those make sense. So these are the eigenvectors computed using the eigenroutine. And then this routine here, or this line here, will print out the loadings again. And so it should be the case that this leftmost column of the eigenvectors here, that's one of the eigenvectors, that should be one of the loadings, the first loadings column. And it is. It's pretty accurate, but it's pretty much in agreement, but not completely. There are differences. And then you do start to see this thing I talked about where, the second eigenvector here is the negative of the second eigenvector here, and that's fine. That happens a lot. That's also true for the third one, not for the fourth. So eigenvectors 2 and 3 have the opposite signs for the 2 different algorithms. And that's fine. That happens a lot. And you just have to kind of be aware that that's okay. Okay, so again, there were some weird discrepancies there. And there's another routine in R, which I believe is the preferred one. We'll talk about that again, I think. And that one is called PR comp, right? And you run it in the following way. And so I'm going to call its output alternative or alt PCA iris. I really shouldn't be using this dot notation. It's very dated. And so I've done that. It's relatively quick. And let's see, again, if it's consistent or if it's more consistent. So we'll look at its standard deviations, and there they are. And we'll compare those to the square roots of the eigenvalue results. And here they are in exact agreement to their first 7 digits. So this is more consistent with the eigenvalues routine. Now, does that mean it's right or more right? I don't know. It just means that it's more consistent with the eigenvalues routine. All right, and so to get the eigenvectors, those are stored in a matrix called rotation, or in a field called rotation. And that should make a little sense because that's what that matrix of loadings does a bunch of projections and effectively rotates vectors. And so here's what it looks like, and we can compare it to the eigenvectors. And I think we'll see better agreement here as well. Yeah, so it looks like these are precisely the same up to however many digits we can see, which is 8 digits here. I don't see any differences. There might be some, but I don't see any. So certainly this routine that we just used now, PR comp, is much more consistent with the eigen routine that you use, that you have used in the past to compute eigenvectors. And the covariance routine, which we didn't really talk about, but is there. Okay, and what were we going to do after this? I've sort of lost track. So we've just looked at the eigenvectors. Let's see, let's try plotting these scores for both routines and see if the principal components similarly make sense for the categorical feature. Okay, let's go ahead and do this. So scores, maybe I'll understand this better once I actually do it. Oh, yeah. So here, sorry, I got a little distracted by trying to read my own code there, or my own comments. So what we're doing now, this is handy. So we've now got these 4 different principal components, and we can plot the data we can plot only the first 2 components as if it's a bivariate problem, and see if we see the same separation of data, and we do. So setosa is over here in this lump. And then over here, there's the versicolor and virginica kind of, again, smushed together. Maybe those separate out better or something if you put on the 3rd axis. But yeah. And lastly, we're going to check to see if the principal components are really uncorrelated. And so to do that, I'm just going to compute the covariance matrix for y. And we're going to make sure that it looks diagonal. So first I do it, and you see a bunch of stuff that's not 0. But if I round it to 10 digits, it's diagonal. And so that's promising. Oh, and double check, are those diagonal elements actually the variances, or rather the eigenvalues? And they are 4.228242. So that's as good agreement as you can get up to the number of digits that I showed. I wonder if I can show 3 more. What if I say 13? That doesn't show me anymore. Yeah. Okay. Anyways, so that's what I wanted to show you here. I want to finish off with something a little bit fun. All this code is in R, but principal component analysis is not something that is so statsy that you don't find it anywhere else. It's in lots of other languages. And so I'm going to switch to another notebook, another Jupyter notebook. So this says Jupyter up here in the top left. And the R logo is there telling you that I'm running R. This also tells you that. I'm going to switch now to a notebook that's running Python. And here's Python logo, 2 snakes or something. And this thing tells you I'm using Python 3. And I'm going to run this on sort of an example you might have seen. I won't go through the details of the Python. So this is all Python code now. I won't go through all the details at the same level that I did for the R code, because I kind of wanted to focus on R in this class. So I'm going to import some packages that I'm going to use a bunch of, and then I'm going to load this data set, which takes a little while. This data set is called the MNIST data set. It's something that you have probably seen even if you're not taking ID 5059. It's a collection of handwritten digits between 0 and 9 made by people and then tagged with what digit they were supposed to represent. So these handwritten things. And so I've just read it in, I don't know if any of you ran into this before, but this was needed due to a change in the fetch OpenML command in the last year or so. If you're using a more up-to-date version of Tom Kelsey in ID 5059 and trying to run his code without that flag as frame equals false, you would have crashed. So I don't know if you guys found that or not, but his code was my old code, but much improved probably from when I threw it together last year. And of course, I hacked it apart from the authors of the textbook's author's code. Okay, so, oh shoot, I'm doing it twice now. Damn, it's a bummer because it takes a little while. Just because it's communicating over the network, and I guess it's a busy place. Those MNIST people sending out their digits all the time to scientists everywhere. It's a super famous data set. Okay, and now for reasons that we don't really need to do here, I got in the habit of splitting the data into testing and training sets, so I'm just going to execute this, but that doesn't really matter for you. I want to look at these individual things. So there's each row of X is a set of pixels. I think it's 28 pixels by 28 pixels is each image size, and each image is a row of X. And so whatever 28 by 28 is, like, I don't know, 700 and something, or some number of hundreds, that's how many elements there are, that's how many variates there are, the number of pixels in each image, right? And so let's take a look at these images. So this is just looking at the first 50 of them in the training set that I made. And so here's one. I think this is probably like a 5, maybe a 3, I don't know. This is going in order, so you've probably seen these exact ones. That's a 0, probably a 4, probably a 1, probably a 9, and so on. Oh, and this thing says what its label is. This little command, this little routine spits out what the actual label is supposed to be. So what was that one that was kind of weird? Yeah, that was a 5. Okay. And so on. So you can look at all these if you want. The first, whatever I printed here, 50 of them. Excuse me. My little mute button for the microphone is not really working. Okay, so yeah, so this is what these guys all look like. But what is important here is, so here's the number 1, right? This is made out of whatever it is, 800 or 700 pixels, right? But most of those pixels are just plain white, so they don't have any information in them whatsoever. And in fact, that's true for most of the digits. So like all the pixels along the perimeter, say, are basically not used. And so you can check this claim by adding up all of the images together and seeing what you get if you smush them together into one single image. And so that's what this does here. So this is all of the training data, which was how much? 5,000 images. So this is adding up 5,000 images together. And so that's not one digit, right? Maybe it's kind of 3-ish, kind of 9-ish, kind of 8-ish. I don't know. It's all kinds of things. But what you can certainly see is like the first 3 or 4 columns of the pixels are useless. And the last maybe 3 columns are useless. And the first 3 or 4 rows are useless. And the last couple rows are probably useless. And so we should be able to see that with principal component analysis. We should be able to see that. So what is it? These are 28 by 28. So for at least 100 of these pixels, we should be able to just ditch them because they don't carry any variation of the data. So we should be able to look at principal component analysis and see that we only need whatever smaller number of pixels. So we're going to try that. Right, but we'll use Python. This is all Python here. We'll use Python's PCA routine. It's part of scikit-learn, at least the one I'm going to use. And it works like this. You have to manually center the data for this one, I believe. Otherwise, I think you might get into trouble. And then I'm going to fit this model and run it. You can look at this code if you want to know how the Python stuff works, but that's kind of not my point. So now let's look at the relative contribution of each principal component to the total variation. All right, so I'm going to plot what they call the explained variance ratio. Right, so that's the proportion of variance, and I'm going to make a plot of it. So this is what we call P sub k, right? And so sure enough, as k grows and it goes up to whatever it is, 700 and something, almost 800, the proportion of variance explained plummets fast, right? So the first few principal components are really, really important. But as you go further along, not really important. Now, those principal components don't necessarily represent one of the pixels, remember? But the number of them is the number of pixels. And so you can strip this problem down, probably, according to this, to maybe the first 100 dimensions. So that instead of a multivariate problem with 800 variates, you could probably do fine. You probably wouldn't do any better than if you kept all 800 than if you kept the first 100 principal component axes. So that's a big difference, right? So that's a big help. You can also do a cumulative version of that thing, and I'll show that here. It doesn't look much different. So it reinforces it. So this is when you sum up, and this asymptotes to 1 as opposed to 0. And in both of them, you see, like, yeah, maybe the first 100 would be fine. Or maybe, I don't know, at least I could throw out the last few hundred. Yeah. All right, that's all I wanted to say to you today. I hope everybody is well, and I hope that this new recording method worked out. Yeah.
So that's just the first sample, a sort of taste of using principal component analysis. We did it in 2 different languages. Hopefully you got some insights about what's going on. And we're going to do a fair bit more of it in the lectures to come. I'll see you then.